Welcome back to the Automotive Cybersecurity Education Series. This is Episode 11, Sensor and Actuator Security. In modern vehicles, sensors are not just measurement devices. They are the eyes, ears, and balance of every driver assistance feature. And when those eyes can be fooled, the whole car can be fooled. Today, we will look at how attackers do exactly that. So why are sensors suddenly the new attack surface? The answer is simple. Modern cars trust their sensors more than ever. A typical Level 2 vehicle has more than 50 sensors. Cameras, radars, lidars, ultrasonic sensors, GPS, IMUs, and tire pressure sensors. Every one of them feeds safety-critical decisions. But here is the problem. Sensors operate in the physical world. They cannot tell the difference between a real signal and a malicious one. A bright laser, a fake GPS signal, an ultrasonic tone. These are not software bugs. They exploit physics itself. And that means classical IT security cannot stop them. This is why sensor security is now a major topic in ISO 21434. Here is what we will cover in the next 10 minutes. First, camera and lidar spoofing. Second, GPS jamming and spoofing. Third, IMU acoustic attacks. Fourth, TPMS vulnerabilities. Fifth, sensor fusion attack surface. And finally, defense strategies and standards mapping. Let's begin with the most visible sensor of all, the camera. Cameras are the cheapest and most widely used perception sensor, but they are also the easiest to fool. 3 attack types matter most. The first is the adversarial patch. A small printed sticker on a stop sign can make the classifier read it as a speed limit sign. The patch looks meaningless to humans, but the neural network sees something completely different. The second is the phantom attack. This was demonstrated by Nasi and team in 2020. A projector flashes a fake pedestrian on the road for just 100 milliseconds. The Tesla autopilot reacted with emergency braking. Drivers behind would never see the cause. The third is sensor blinding. A strong infrared or laser source saturates the image sensor. The camera goes blind. Object detection fails completely. None of these attacks need network access. They only need line of sight to the camera. Now let's talk about LiDAR. LiDAR is often considered the most reliable perception sensor. But research from 2024 proved otherwise. 2 attack types are now well documented. The first is object injection attack, or OAA. The attacker fires precisely timed laser pulses at the LiDAR receiver. The LiDAR interprets these pulses as real reflections. A phantom car or pedestrian appears in the point cloud. The second is object removal attack, or ORA. Here the attacker overwhelms the receiver with synchronized pulses. Real obstacles disappear from the point cloud. This is more dangerous because the vehicle does not see the threat at all. A study at the University of California, Irvine showed this on first-generation LiDAR systems. Newer LiDARs now use pulse fingerprinting and timing randomization to defend against this. But many cars still on the road use older sensors. And in 2025, researchers showed that even SLAM-based localization can be tricked. A simple mirror, placed at the right angle, induced over 4 meters of position error. This is the new reality of perception security. Next is GPS, short for Global Positioning System. GPS signals from satellites are extremely weak by the time they reach the ground. That is why they are easy to attack. 2 attack modes exist. Jamming means broadcasting noise on the GPS frequency. The receiver loses lock and cannot compute a position. Spoofing is more subtle. The attacker transmits fake but valid-looking GPS signals. The receiver still works, but it now reports a wrong location. The hardware needed is shockingly cheap. A HackerF software-defined radio plus open-source GPS SDR SIM costs around $300. In 2019, Regulus Cyber demonstrated this against a Tesla Model 3. The car drifted off the highway because navigation believed the spoofed location. For trucks, robotaxis, and any vehicle relying on lane-level GPS, this is a real safety risk. Defenses include multi-constellation GNSS, inertial cross-checks, and RAIM monitoring. Now we move to the Inertial Measurement Unit, or IMU. The IMU measures acceleration and rotation using tiny MEMS structures. Those structures vibrate at specific resonant frequencies. And here is the weakness. If you play a sound at exactly that frequency, the MEMS element resonates uncontrollably. The IMU outputs garbage data. This was demonstrated in the famous Walnut paper at USENIX 2017. The attack used frequencies between 18 and 28 kilohertz. The transducer cost about $5. For a vehicle, this means stability control, rollover detection, and dead reckoning can all be disrupted. Even autonomous valet parking, which depends on IMU for localization between GPS fixes, can fail. The defense is acoustic shielding plus signal validation against other sensors. But many ECUs today have no acoustic protection at all. Let's talk about the most overlooked sensor, TPMS. That is the tire pressure monitoring system. TPMS sensors transmit at 433 MHz in Europe and Korea, 315 MHz in North America. The signals are unencrypted and unauthenticated. Each sensor has only a 32-bit ID. Researchers Roof and team showed this back in 2010. You can track a vehicle from up to 40 meters away just by listening to its TPMS. You can also inject false low-pressure warnings. That triggers driver alerts and even forces some safety systems to activate. Why is this not fixed? Because TPMS sensors are mass-produced, battery-powered, and replaced every 5 to 10 years. Adding cryptography means redesigning the entire ecosystem. For now, TPMS remains a privacy and nuisance attack vector. So why not just fuse all the sensors and rely on majority voting? This is the false sense of security. Sensor fusion does help, but only if the sensors fail independently. The problem is that most fusion algorithms weight one sensor heavily. For example, LiDAR dominates obstacle detection. Camera dominates lane keeping. GPS dominates localization. If you attack the dominant sensor, fusion does not save you. Worse, some attacks are coordinated. Spoof the camera and the LiDAR at the same time, and the fusion logic confidently outputs a wrong result. This is called consistent spoofing. Real defense requires cross-modal anomaly detection. An honest acknowledgement that fusion is a mitigation, not a guarantee. Let's put this together in one feasibility table. Camera attacks need very low cost and only line of sight. LiDAR attacks need moderate skill and synchronized pulse hardware. GPS spoofing is cheap and can be done from a parked car nearby. IMU acoustic attacks need physical proximity and tuned frequencies. TPMS attacks are easy but limited in safety impact. The pattern is clear. The cheapest attacks have the highest practical risk. This is why these threats are no longer hypothetical. So how do we defend? Think in 4 layers. Layer 1 is the sensor itself. Use pulse fingerprinting on LiDAR. Use anti-blinding filters on cameras. Use MEMS with mechanical damping. Layer 2 is signal validation. Compare GPS with wheel speed. Compare LiDAR with radar. Detect physically impossible jumps. Layer 3 is fusion-level anomaly detection. Machine learning models can flag inconsistent sensor states. Layer 4 is system response. When sensor integrity is in doubt, the vehicle must enter a safe degraded mode. No autopilot, no ADS, just human control. The point is, there is no single silver bullet. Defense must be layered, just like in classical IT security. How does this map to standards? UN Regulation R155 lists 69 attack vectors in Annex 5. Several apply directly to sensors. Threat 16 covers threats from sensor manipulation, a direct match for camera and LiDAR attacks. Threat 17 covers cyber attacks via short-range wireless TPMS at 433 MHz, falls right into this category. Threat 26 covers manipulation of vehicle telematics. GPS spoofing affects telematics and e-call accuracy. Threat 28 covers threats from intentional jamming or blocking GPS, TPMS, and V2X jamming. All map here. ISO 21434 requires that all of these be analyzed in your Terra. That means damage scenarios, threat scenarios, and risk treatment for every sensor input. If your Terra does not include physical layer attacks, your assessment is incomplete. This is something I see often as an ISO 21434 lead auditor. Let's summarize. First, sensors are the new attack surface, and physics-based attacks are real. Second, fusion helps but does not guarantee safety. Third, defense must be layered across sensor, signal, fusion, and system response. Fourth, your Terra must include physical attack vectors. In Episode 12, we will switch from threats to standards. We will look at UN R155, R156, ISO 21434, J3061, China GB, and Thai SAX. That is the regulatory map every automotive engineer must understand. Thank you for watching and see you next time.